student at Seoul National University, and I'm very happy to speak here. Today, I would like to talk about dice rolling game on a set of Toruses. This study is with Jiu Kang and my advisor, Seoul Kim. Some of you guys know fiber game is a puzzle game in which you need to flip over all the counters so that your n by n board changes from being completely full of white pieces and instead becomes entirely inhabited by black pieces. Clicking on any counter will not only flip over that piece from being white to black, but also it's for neighboring pieces immediately above, below, to the left, and to the right of that piece you clicked. We reserve their alliance, becoming white if they were black, black if they were white. For example, if I click this, then the board becomes like this. Now let's change the rule of game. A moment. Then the fiber game's question is it possible to change from being completely full of white pieces to entirely black pieces? The answer is always yes. So let us change the rule of game. At this time, we identify the edges of the board facing each other. Facing each other. Then we consider an unfolded torus. And clicking on any counter will not only flip over that piece, but also pieces in a consecutive 2x3 subarray, and whose top left piece is the piece that you clicked. If you click this counter, then the board becomes like this. Since it is an unfolded torus, we always flip over 6 pieces. For example, if I click this, then we have this. If I click this, then those 6 pieces are changed to black, since the edges are identified. Then, as you know, white and black colors are considered as elements of G sub 2, and so instead of G sub 2, we use the elements of G sub n. Then, see this example. We locate elements of G sub 3 on 7x7 board, like this. And if I click this counter, then the entries on those 6 entries, then the numbers on those 6 entries are increased by 1. And also if I click this, then the numbers on those 6 entries are increased by 1. And the question is, in this game, given a torus, which is located elements of G sub n, is it possible to have 0 appear on top face of each square on the torus? The answer to this question is not always yes, so we will find the answer in this talk. Now I will define this game formally, named a dice rolling game on a set of toruses. N dice is a dice with n faces such that element I of G sub n is written on the i's face. And given integers alpha 1, alpha 2, we locate alpha 1, alpha 2 n dice in a rectangular array and glue lower and upper together and left and right together. Then we have alpha 1, alpha n dices on the torus, like this picture. Also, we denote by the alpha 1, alpha 2 n the set of toruses on each alpha 1, alpha 2 n dice are located. And for positive integers, alpha 1, alpha, beta 1, beta 2, where beta 1 is less than or equal to alpha 1 and beta 2 is less than or equal to alpha 2, beta 1, beta 2 rolling procedure is rolling the dice, which form a beta 1 by beta 2 rectangular subarray on the torus, so that we increase the number on the top face of each of them by 1. For example, this is a torus in 1983, and the right one is the torus, resulting from going through 2 for-lowing procedures. So as you see, the numbers on these regions are increased by 1. That's the rule of loading in this game. Then we may ask, given a torus, is it possible to have 0 appear on top face of each of R1 to n dice on the torus by repeatedly applying beta 1, beta 2 loading procedure? We call this game the dice loading game on the R1 to n with respect to beta 1, beta 2 rolling procedure, or R1, R2, beta 1, beta 2 n, DR game for short. Also, a torus for which the answer to the question is yes is a solution of the dice rolling game. For convenience, I'll introduce some notations. We denote by n R1 to n the set of matrices with elements in G sub n. And for element A matrix, we denote by square bracket A sub ij the element of G sub n in the ij entry. Also, we assume that the first component and second component for every subscript in this slide are reduced to alpha 1 and alpha 2 in respectively. Also, given matrix AB, addition and scalar multiplication are normally defined. We denote by A sub ij, a matrix with 1 in the ij entry and 0 as well.
What is the set R? It's color C is in R.
Oh, I'm sorry, that must be G sub n. Oh, that's the point. No, G mod n. And for positive integers m1, m2, k1, k2, J sub k1, k2, m sub 1, m sub 2 is the matrix defined as like this. For example, in this case, k1, k2 means the starting position, and m1, m2 means the size of consecutive rectangular array whose entries are 1. For example, see this, in this setting, J sub 1, 2, 3, 2 is this matrix. The starting position is 0, 0, 0, 1, 0, 1, 2, and so the position of this entry is 1, 2, and the size of rectangular array whose entries are 1 is 3 by 2. Especially if the size of rectangular array whose entries are 1 is beta 1 by beta 2, we denote it by J star. That's the beta 1 beta 2 loading procedure in the game. And also, we associate a torus with a matrix in whose ij element equals the number on the top face of n dice in ij entry of the torus. So it is sufficient in order to characterize the solutions of the dice rolling game, it is sufficient to characterize the matrix whose corresponding toruses are solutions of the DR game. So in this reason, if A, for matrix A, if A can be the 0 matrix by adding a linear combinations of J star, then the torus corresponding to A is also a solution. And so A is a solution matrix of the DR game in this case. Also, A is a solution matrix if and only if there exists Cij. A plus summation Cij, J star ij are 0 matrix. We call matrix Cij a solving coefficient matrix of the DR game corresponding to A. Now we will characterize the solutions of the DR game. Let Gi be the greatest common divisor, alpha 1 and beta 1 for each I, and let beta 1 equal S sub I, G sub I for some positive integers. Then we will define three kinds of metrics. For integer ij, we will define Cij, Rij, Qij like this. And as you see, Cij and Rij are defined to be a linear combination of J star, and so they are solution metrics in DR game. And so, since C is a linear combination of J star, Q is also can be represented by a linear combination of J star. And so, those three metrics are all solution metrics. The definition is a little complicated, but we have more simple formula in the following. And we will using those three metrics instead of using J star. First, the Cij. For example, in 6A245 DR game, most of you forgot the notation, but C27 is this matrix. By the definition, C27 is this the linear combination of J star. That is, Cij equals this formula. This formula means if J satisfies this condition, then Cij is the zero matrix. If not, Cij has this form. Recall that G sub 2 is the greatest common divisor of alpha 2 and beta 2, and similarly G sub 1 is the greatest common divisor of alpha 1 and beta 1. And the ij entry of Cij is -1, and there are beta 1 consecutive entries which are -1. And there are also consecutive entries which are 1. And the starting position is I W sub j entry, where W sub j is the least non-negative integer, which is congruent to j modulo g sub 2. Cij has this form. Cij, that is Cij has non-zero 2 columns. And also we can obtain this formula by algebraic computing. Now Rij can be represented by this. This is example Rij. R54 is this matrix. R54 has 2 non-zero rows. More precisely, Rij has this formula. It is also mean if I satisfy this condition, then Rij is the zero matrix. If not, Rij has this form. There are 2 non-zero rows which are beta 2 consecutive entries. The ij entry of Rij is -1, and these are 1s. The position of this entry is Uij, U sub ij, where U sub I is the least non-negative integer congruent to I modulo G sub 1. Last, Qij. And Qij, for example, Q37 has only 4 non-zero entries, 2 1 and 2 -1. More precisely, Qij equals this formula. And if I satisfy this condition, or J satisfies this condition, then Qij is the zero matrix. And there are 2 1 and 2 -1, and all the other entries are 0. And the ij entry of Qij is 1. And also this formula can be obtained as like this. Now we will define 2 kinds of function t and s. There are many definitions, and this is definition of function t. Function t and s will play important role in our main theorem. So this is the definition of t. First observation, note that Qij can be represented by a linear combination of J star. And so A is a solution matrix if and only if T of A is a solution matrix. And the other observation, the Ij entry of T of A is 0 if I is greater than G sub 1 and J is greater than G sub 2. That is, for example, see this matrix and consider this matrix A minus negative minus A, the entry of A26 and Q26. Then the 2,6 entry of this matrix is 0, as you see. 2,6 entry of A and 2,6 entry of Q26. So T of A has this form. That is, the entries in this area are 0. In other words, the entries in blue area are 0 in T of A for any A. And the function S, this is the definition for the function S. The notations are a little complicated, but the meaning is simple. The function S is a function for making entries in these red areas appear 0, always, if it is possible. And in previous example, S of A is computed like this. And since it is possible, in SA, the entries in this area becomes 0. This is our main theorem. By using the function T and S, we characterize the solutions of the dice bowling game as like this. A matrix A is a solution if and only if T of A and S of A are computed as like this form. This theorem says that it is sufficient to compute function value T of A and S of A to determine it is a solution or not. First formula. See the first formula. This formula means the entry of this blue area must be 0, and this area has identical rows, and this area has identical columns, and also each entry in this area is multiple of S of 1, and each entry in this area is multiple of S of 2. And second formula, S of A means entries except in yellow area. Entries except in yellow area must be 0 in SA, and entries in yellow area are identical and they are multiple of S1, S2. This is our main theorem. In previous example, for this A, TA is computed as like this. That is, the entries are this area are 0, and this area has identical rows, and this area has identical columns, and they are all multiple S1 or S2. But in this case, S1 and S2 are 1. So it satisfies the condition of our main theorem. And also SA, the entries except this are 0. And the entries in this area are identical and multiple of S1, S2. So A is a solution matrix by our theorem. In addition, we can compute the serving coefficient matrix of A, but it is tedious, so I just skip it. So the idea is the definition for T of A, and these are definition for T of A and S of A. By adding these two equations, then we obtain this. Combining this equation and the resulting of our main theorem, then we can compute a solving coefficient matrix of A. Actually, we obtain this. It is a solving coefficient matrix of A. Now, we give a necessary and sufficient condition for torus, which is a solution in dice rolling game. It is a two-dimensional case in some sense. So we can think about a one-dimensional case. That is, if alpha 1 equal beta 1 equal 1, a matrix in this becomes an alpha 2 tuple, which are circles on each of which alpha 2 n dice are located. For example, this is a circle with 12 dice, and the left one is a circle resulting from by rolling those 4 dice. So the numbers on those 4 dice are increased by 1. Then also we can ask, given a circle, is it possible to 0 appear on all the dice by rolling given procedure, by applying given procedure? So if we apply before we apply our theorem, consider the case that alpha 1 equal beta 1. Then if alpha 1 equal beta 1, T of A and S of A are computed as like this, more simple than general case. So this is a characterization for the solution matrix of Toruses when alpha 1 equal beta 1. It is a characterization by just applying our main theorem. However, we found that this condition implies this condition in case that alpha 1 equal beta 1 by algebraical computing. It does not need to difficult skill, but it is hard to find it actually. And so the previous characterization are simplified as like this. And so we obtain a characterization for the dice rolling game on a circuit like this. Our characterization of two-dimensional case will be generalized to t-dimensional case, I believe it. And that's all. Thank you for your attention.
Questions or comments?